We will be discussing the applications of ensemble formalism with some classical examples. So similar discussions were done in the case of canonical ensemble also, where we discussed the same example. So the first example will be that of a classical ideal gas, and hope you remember that I had mentioned in the very beginning of our statistical mechanics course that we will be using familiar systems like classical ideal gas and harmonic oscillator as the testing systems to check the validity of the theory that we are developing. And once we are able to establish the well-known results of these systems like classical ideal gas or the harmonic oscillator, which are very familiar to us for any physics student or physics people, we will be able to build on the same formalism to be applied on any other maybe complicated problems as well. So as usual, we are starting with classical ideal gas as a application of the grand canonical ensemble formalism. Okay, now we have the preliminary discussion of our ideas regarding classical ideal gas. We know that it's a system of non-interacting gases, and now we consider the classical ideal gas system having a volume V, means enclosed in a container of volume V, to be a member of the grand canonical ensemble. Of course, the macro state of the system will be defined by mu Vt, where mu is the chemical potential, V is the volume of the container, and T is the equilibrium temperature of the system. Now, we have to begin with the grand canonical partition function. And in the previous discussion, we have seen that the grand canonical partition function can be expressed in terms of the canonical partition function, okay, by introducing fugacity and all small set. So we will just start with the canonical partition function of the classical ideal gas, which is familiar to us from our earlier discussion. So the canonical partition function, I am writing P of classical ideal gas. It's given by, we have been writing it as QNVT, because NVT is a macro state of the canonical ensemble systems. So that was equal to, for an n particle system, we wrote it equal to, in terms of the single particle partition function, Q1 of Vt. So Q1 of Vt, that was a procedure that we adopted, you can refer back, raised to n divided by n factorial. So this was the expression that we have used for the canonical partition function for classical ideal gas containing n number of particles, where what is Q1 Vt, where Q1 of Vt, simply you can write as Q1 is nothing but the single particle partition function. That was a methodology that we have been following. We first calculate the single particle partition function, and since the particles are independent and non-interacting, the partition function for the entire n particle system can be taken to be as the product of all these single particle partition functions, Q1 into Q2 into Q3 etc. up to n particles. And since all the single particle partition functions are the same, or having the same value, it can be written as Q1 raised to n. Okay, single particle partition function. And what is the role of this n factorial? See, the n factorial is to account for indistinguishability of particles and hence to avoid the Gibbs paradox. So it's a correction for Gibbs paradox, otherwise known as for the correct Boltzmann counting. So that is the idea. Now, so we start our discussion from the definition of canonical partition function for classical ideal gas. Right now, since what we are going to do, Q1 in equation number 1 is a function of you can see V and T. Okay, and in the case of classical ideal gas, since the particles can be anywhere in the space available to them, we can say Q1 is always proportional to V directly. Okay, so that's the thing. So what we are going to do is that we are going to separate the dependence of functional dependence of Q1 on volume and the temperature separately. We are going to take them separately. So this is the reason, since the particles belonging to the system can be anywhere means the entire volume V of the container is available to the particle. That's what we mean. Can be anywhere in the space available to them. Space available to them. The dependence on volume will be directly proportional to that Q1. So available to them, we can write Q1 will be proportional to, we can write Q1 is proportional to V, the entire volume V. So that we have just written Q1 is a function of V and T, and we can see the function dependence is directly proportional to V. Okay. Therefore, we can write Q1 of Vt can be now written specifically as, I'm separating out V, okay, then I'm multiplying with a function of T. So this is a modification that we are bringing in here. So what is the modification? Q1 is in general a function of V and T. And since the entire volume is available to every particle of the system, we are taking Q1 is directly proportional to V, that is the dependence, and then Q1 can be written as V into function of T. Means we are separating out the functional dependence on volume and the functional dependence on temperature. Okay, and f of t can be of any form which depends upon see the assumption that we are making. For example, f of t can be like see in one particular case that f of t, if you assume that f of t is proportional to some t raised to n, or we can say that if n is equal to 3 by 2, then t raised to 3 by 2, then you will be getting our standard results. So that we can see at the end. So V into f of t, where f of t is the separate function, which is a function of the temperature alone, right? So where f of t is a function of the temperature alone. So let me specify that where f of t is a function of temperature alone. So we have separated out that function dependence on volume and temperature in Q1 Vt, temperature alone. Okay. Now we are in a state to write down the grand partition function of the system. Therefore, the thermodynamics system will be obtained from the grand partition function or from the Q potential of the system. Okay, so the grand partition function, I'm writing grand partition function of the system. Which is a system? The classical ideal gas system. Okay, that's the definition. We can write that one in terms of the grand partition function can be written in terms of the fugacity, right? So z equal to, script letter z is equal to sum over sigma nr equal to 0 to infinity. Hope you remember this expression from our earlier discussions. Z raised to nr, which z? The fugacity, small z raised to nr times qnr qnr of Vt, of course, okay, where qnr is the canonical partition function that is given by equation number 1. In place of n, we have written nr, that's all. Okay, so which we can substitute, that's equal to sum over nr equal to 0 to infinity, sum over nr running from 0 to infinity, then z raised to nr, the fugacity raised to nr, into, can we substitute for qnr from equation number 1 using equation number 2, that is, I can write q1 vt, I will substitute for q1 vt, I will use a square bracket, that is v into f of t, that is q1 vt by equation number 2, v into f of t divided by z, is not by equation number 1, I should divide by n factorial, but here instead of n we have taken nr. Because the value of nr can be different, so I will be writing in place of n factorial nr factorial, right? So which can be again rewritten or modified as sum over the same quantity nr equal to 0 to infinity, of course, that is here z raised to nr is of course, one more thing, see, raised to n is here in equation number 1, so I have to raise this thing also raised to nr. So now both z and the second term is having raised to nr, so I can just club it together and I'll be writing this one is equal to, I'm taking the z inside the bracket, z v f of t whole raised to nr divided by nr factorial. divided by nr the factorial. Okay, so that becomes our equation. Now this one can be again simplified. This one can be again simplified and written as an exponential function, that is e raised to, which is equal to e raised to simply set v f of t. Okay, so I'm calling that one equation number three, running number 3. So that is e raised to set v f of t. And how come that one? That is due to one of the series expansion that we have already used in one of the earlier discussions. What is that? So we have an the series expansion of the e raised to x. What is e raised to x equal to? E raised to x can be expanded as a series, that is sum over n equal to some 0 to infinity. X raised to n, hope you remember we have used it earlier also, x raised to n divided by n factorial. So this is a series expansion for e raised to x. So now in our case, if you substitute x equal to zv f of t, if you substitute x equal to, you treat this one as x. Now you can see that it is of that form of the series expansion. So the answer is going to be e raised to x or e raised to zv f of t. So that is a simplification that we are able to do. So equation number 3 gives you the grand partition function of the system in terms of the fugacity z, the volume v available to the system or the particles, and f of t, which is a functional dependence of the temperature of the system. Now let's carry on. Now, once you get the grand partition function of the system, you will be able to get the Q potential of the system, which acts as the bridge, right? So the Q potential of the system, hope you remember how we defined the Q potential of the system. The Q potential of the system was defined as the logarithm of the grand partition function, okay, of the system, as per definition, is given by Q equal to log Z. Q is equal to simply log of the grand partition function. So which is equal to, and we have proved that that is once again equal to PV by KT, right? And by equation number 3, log Z, log of e raised to Z v f of t, its natural logarithm. So you'll be finally getting this is equal to Z v f of t. Z v f of t, because log of e raised to Z v f of t will be equal to simply Z v f of t. Right? So what happens here is that the volume can be cancelled on both the sides. Okay, so let me call this one as some equation number 4. It will be handy for us later. So that is equation number 4. Now cancelling those two things, I will be getting one more equation for the pressure of the system first. That is equal to, I can cross multiply, that is equal to Z into KT, multiplying KT on the other side, times f of t. Remember already that one temperature dependence has come from KT, and there is yet another temperature dependence that can come from what is known as f of t, which is defined as a function of temperature alone. So let me say that this is equation number 5. So that gives you the pressure of the system. Okay, again, if you want, you can just say that this is the expression for the pressure of the system in grand canonical ensemble. Now, same manner, we can calculate the average number of particles. Okay, that's also a very important quantity here. See, also average, these are the thermodynamical quantities of interest. Average number of particles. Why we are discussing about the average number of particles in a grand canonical ensemble? Because in a grand canonical ensemble, as we have seen, both the energy of the system as well as the number of particles in the system are varying or fluctuating. So since they are fluctuating, we can only what we can measure is only the average value. You cannot take the definite value because it's varying. So average number of particles of the system, that is denoted by n bar, or you can simply call it as En. En is equal to, we had obtained the equations for En from our thermodynamical calculations we had done earlier. So that is equal to N dou by dou Z, where Z is the, remember that this Z is the fugacity of Q potential, that is log of capital Z. Okay, so which we can substitute, because we have already got what is log Z. Log Z equal to, by equation number 4, that is Z v f of t. So I can write this is equal to Z into dou by dou Z of what do you call Z v f of t. F of t is a function of temperature alone, so and volume is independent. So you are going to get the result finally as, so this is equal to finally z outside is remaining, and dou by dou z of the other thing is what you get is z v f of t itself you are getting back. So let me say that this is your n bar. So that is my equation number 6. All these are results. Please remember, this is a result, this is a result, and this also is a important result in for the system, right? Since f of t is not defined now, depending on the nature of the f of t, you will get some equation for all these quantities. Similarly, you can calculate the internal energy of the system. Similarly, internal energy of the system. Hope you have already understood why we are discussing all these quantities, because all these quantities are the thermodynamical quantities which we have to verify for any system. The internal energy of the system, how the internal energy was related in grand canonical ensemble. Hope you remember that was equal to minus dou by dou beta of log z, which we proved to be equal to simply kt square dou by dou t. Right, that was the expression in the summary of thermodynamics. Kt square dou by dou t of log of z. Okay, kt square dou by dou t of log of z. You have to refer back to our conclusions or summary of thermodynamical equations, and we will have to use that one here. So that's equal to, finally, that's equal to kt square into dou by dou t of what is log z. Once again, from equation number 4, log z can be replaced with fugacity z into v into f of t. Okay, v into f of t. Now you know that here we are doing derivative, partial derivative with respect to temperature. So since the value of f of t is not explicitly taken, we can write the derivative of f of t can be represented as f prime of t or f dash of t. Okay, depending on what is f of t, you will be getting an f prime. That's not a problem for us. So we can say that this is nothing but equal to, finally, kt square, z is also there, it's coming out, and of course that v will be also treated as a constant. Then what is remaining is derivative of f of t will be some f prime of t. So we can say that this is my equation number 7, that will be giving the internal energy of the system. So depending on the value of f of t, the nature of f of t, you will be getting an expression for the internal energy of the system. Okay, now the same manner, what you can do, you can just you got both p and n, you got both p and n. Okay, so since you have got both p and n, I can just take so consider the ratio of equation number 5. Equation number 5 was for what you call pressure, and I'm dividing the equation for a number of particles. Okay, that is 6. So what was the equation number for equation 5? Equation 5 was, yes please, here equation number 5 was just p equal to set kt f of t. So let me write that p equal to see, that gives p equal to set fugacity kt into f of t, some function of time, divided by equation number 6 is for n bar. N bar is nothing but en. So that's equal to, what is n bar? Set v f of t. That is set v f of t. Set v f of t. Let's see what will happen. So of course the set and set will be getting cancelled. This f of t and f of t, whatever be the value of f of t, that will be also getting cancelled. So what you're left with is simply kt by v. And now can we just cross multiply that one? So on cross multiplying, what you'll be getting? You'll be getting simply pv is equal to, n bar is nothing but n itself, n kt. And you know that this is nothing but the equation of state for classical ideal gas, which is nothing but the equation of state for classical ideal gas. So we are able to establish the classical result, classical ideal gas. Even without assuming what is the exact nature of f of t, we are able to establish the classical idea. You know, this pv equal to nkt is yet another form of pv equal to nrt. Okay, so pv equal to nkt and pv equal to nrt are both are the same actually. Okay, because you know that this r is equal to n by na, right? So that was the definition. Okay, so you can just get all these expressions interrelated. Okay, then what you can do is that just you can write sorry, I just committed a mistake. This n is equal to n by na. Okay, and you will be getting kb also there. So that is equal to n by na into rt. Okay, and this r by na, right, r by na is defined as what? kb, the Boltzmann constant. So it will become en, okay, sorry, capital En into kbt. So n kbt. So both are equivalent. That's the thing. Now, see, having established the equation of state, you can stop here, or let's derive two more important things. One is the Helmholtz free energy. Of course, similarly, the Helmholtz holds free energy of the system energy. We can get it as A is equal to, as we had obtained, that was equal to nkt log z. This was what we have established earlier, minus kt log z, minus kt log z. So that is equal to, first term I will be keeping as such, nkt log fugacity minus kt. In this case, log z is equal to zv f of t. zv f of t. We can keep it as such because f of t is not taken directly. So that also can be. Similarly, you can get entropy. Similarly, entropy. All quantities of interest can be obtained. Entropy. So entropy S is equal to U minus A by T, which you can substitute here. So that will be equal to U is equal to, we already had obtained that U, that is KT square Z into V F dash of T. Hope you remember that was an earlier equation. Then minus A we have obtained by this equation. So that is nkt, once again nkt log z. Okay, then minus will become plus, that is what, ktz v f of t, right, whole divided by t, So what will happen, that the t will be getting cancelled everywhere. So here one t will be gone, here one t will be gone, here also one t will be gone. So that's getting cancelled by this t. So what is remaining here is minus nk log z, minus nk log z. This is the factor that I'm writing. Then plus, we can take some common factor like zvk, zvk, both are common. zvk is common, zvk is common in both first and last term, so I'm taking as common. So what remains is that t into f dash t, that is obtained from the first term, plus what, the f of t. So that is, so once you know the value of f of t, you will be able to do that. And similarly, you can prove that the heat capacity Cv can be proved to be equal to some 3 by 2 nk. Cv can be proved to be equal to Cv 3 by 2 nk, the value that we usually use, provided f of when or if f of t is assumed to be of proportional to t raised to 3 by 2 or t raised to n. Okay, so depending on the value of assumption for f of t, you'll be getting back this particular familiar equation for the Cv as well. So that's about the application of grand canonical ensemble formalism to discuss the familiar case of classical ideal gas. Okay, so we will continue with the examples of harmonic oscillator, which is yet another familiar system, and I think that will be done as a separate lecture. Thank you.